Greetings and salutations, magical chemists. Today let's talk about different types of electrochemical cells and how to calculate their cell potential. There are technically only two types of electrochemical cells that you need to know, but one of them has two names. This is the voltaic or galvanic cell. Basically, this is a battery. It's a thermodynamically favorable or spontaneous redox reaction which we can use to generate electrical energy in the form of an electrical current. An electrolytic cell is not spontaneous. It is thermodynamically unfavorable, and it actually requires electrical energy in the form of a current to run it. In short, galvanic cells, or voltaic cells, produce current, while electrolytic cells use current. Now let's talk about how you can measure something called the cell potential. Of course, you still need to remember that oxidation is the loss of electrons and reduction is the gain of electrons, because that's going to come in very handy. Now, cell potential, otherwise called E-cell, is a measure of the potential difference between two half cells. That's basically how much voltage exists. This potential difference is caused by the ability of electrons to flow spontaneously from one half cell to the other. The cell potential is basically a quantitative or numerical description of the driving force behind an electrochemical reaction, pushing electrons through the wire or external circuit. Now, much of the time, we're going to be working with a standard cell potential, E0 cell. This, of course, means that we're just measuring the cell potential at standard conditions. Standard conditions for an electrochemical cell is 1 atmosphere, 1 molar solution, and room temperature, 25 degrees Celsius. And we just use that little superscript naught sign, little tiny zero, right, to show that it is standard conditions. And then we tend to measure E-cell in volts, where 1 volt is equal to 1 joule per coulomb. Luckily, the cell potential is actually really easy to calculate. To find the overall cell potential, you literally have to add up the oxidation potential of the oxidation half reaction plus the reduction potential from the reduction half reaction. Now, it's important to note, the more positive the value of E-cell, the greater the driving force, which means it is more thermodynamically favorable the more positive the value. Now, important thing to note, we, of course, have balanced redox reactions, and you sometimes have to multiply to make sure the electrons being transferred are equal. But do not change the cell potentials. It's an intensive property. That means it actually doesn't matter how many times the reaction runs. Now, you can look up in your textbook, which of course you have online access to through Mastering Chem, to find a table of standard electrode potentials, or in Zoomdoll, which is the textbook I have in my room, or it's even in the back of the booklet. So you can find a list of reduction potentials at the back of your booklet and in, well, basically any AP Chem textbook. Now, you might remember that these are a table of standard reduction potentials. So you have to reverse the sign of the reduction potential to get the oxidation potential before you add them together. Also, if you have a spontaneous redox reaction, your overall cell potential must always be a positive value. So that means it's easy to check your math. A galvanic or voltaic cell should always have a positive cell potential. That means whichever metal has a greater or more positive reduction potential, it's going to be reduced. And then the other metal is going to be oxidized. If, however, you have a non-spontaneous redox reaction, your overall cell potential will be negative. This is, of course, what happens in an electrolytic cell. For that to happen, the metal that has the greater or more positive reduction potential, well, that means it's going to be oxidized. Gasp. And as we talked about previously, you can actually use a reduction potential table as an activity series. In a spontaneous reaction, the metals with a lower reduction potential are more active, and they're going to replace the metals with a more positive potential. But remember, that's only what happens in a spontaneous reaction. All right, let's go ahead and try some practice problems so we can see how this goes. Okay, it says consider the half reactions shown below and the standard electrode reduction potentials that follow. Now I want you to notice they have not labeled these as reduction or oxidation, but you are still expected to know that these are reduction half reactions. And here's why. The electrons are reactants, and the electrons are only reactants in reduction. Now, the first problem asks us to write the balanced redox reaction for copper and aluminum that is thermodynamically favorable, aka spontaneous. So our first job is to figure out, well, I mean, clearly they can't both be being reduced. We have to have somebody getting reduced and somebody being oxidized. So who is going to be oxidized? This is where you always want to remember. In a spontaneous reaction, the thing with the highest reduction potential gets reduced. Now, both of these numbers are negative, of course, but one is still a higher value than the other. So it's not positive, but it's closer to being positive than the other one. So that's why it turns out your zinc is in fact going to be reduced in this given reaction. So that means negative 0.76 volts is your reduction potential. But that means you're going to have to flip the other equation because aluminum is going to get oxidized. To find the oxidation potential for when we flip the reaction, it's easy. Just change the sign. So it becomes positive 1.66 volts. And then when we're balancing the reaction, we just straight up flip that aluminum reduction reaction so it becomes an oxidation half reaction. Now that we've done that, we're ready to write our balanced reaction. But you know how to balance a redox reaction, so you should totally try to balance the redox reaction below. And when you are ready to check your answer, unpause the video. And there you have it. Notice you had 3 electrons in one half reaction, 2 electrons in the other half reaction. So our least common multiple was 6. The last step is to calculate the standard cell potential, and that's the easiest part. To find the cell potential, you're literally just adding your reduction potential and your oxidation potential, and that's it. Notice, I am not multiplying them by 2 or by 3, even though I had to multiply to balance my reaction, because your cell potential is an intensive property. And this is a great place to make sure you're doing it right, because remember, this was thermodynamically favorable, so we should have a positive cell potential, and we did. Always a good sign. Now the second question is going to be a little bit easier because we already did the first question, because this one wants the balanced redox reaction for copper and aluminum again, but this time they want the one that is not thermodynamically favorable. Well, if we hadn't done part 1, we'd have to work backwards using the reduction cell potentials like we did at the beginning, but we already did question 1. Since we know what the thermodynamically favorable reaction looks like, the thermodynamically unfavorable reaction is just the reverse. So we just flip the reaction. And to get the cell potential, well, we reverse the reaction, we flip the sign on the cell potential. That's because what was being oxidized is now being reduced, and what's being reduced is now being oxidized. So numerically, we now have positive 0.76 as our oxidation potential, and negative 1.66 as our reduction potential. So that must be the cell potential for the non-spontaneous reaction shown. Okay, we've got a couple more practice problems to try. Let's look at them. The next problem is very similar to the first practice problem, so I totally think you should try this on your own. It does require you to use the reduction potential chart to find the missing reduction potentials for these half reactions, but then once again, we're going to be looking at a thermodynamically favorable reaction. You're going to calculate the E cell. You actually don't even have to balance the reaction. You're literally just calculating the E cell value. So first, take a moment. Your list of cell potentials. Let me remind you what that looks like. It looks like this. It's in the very back of your book. It's on the other side of the formula chart. So find that, determine these reduction potentials, and then calculate the E cell value. When you are ready to check your answers, unpause the video. First, let's check those cell potentials. Make sure you're checking the ion of copper because there are multiple half reactions with copper. And we were specifically looking at copper 2+ gaining 2 electrons. So be careful when you are looking at the multiple reduction potential half reactions. Since both of these have positive reduction potentials, that means the one that is more positive is the one that's actually reduced. And we have to change the sign on the other one to find the oxidation potential. And then to get the cell potential, just add them together. So the cell potential for coupling these 2 half reactions is 0.46 volts. Notice they did ask you, why in the world, how can you justify that this calculated cell potential represents a thermodynamically favorable reaction? Well, it's really straightforward. E's cell is positive, therefore it must be a thermodynamically favorable reaction. Now the next problem is a little bit different. This time we gave you the balanced reaction, and you have to use the balanced reaction to calculate the standard cell potential, E naught, and figure out if this reaction is thermodynamically favorable. All right, I think you should try this. You have enough information to do it, so go ahead and try it on your own. And if you get stuck or when you're ready to check your answer, unpause the video. First, you have to figure out what's being oxidized and reduced in this given redox reaction. Then we need our table of cell potentials. Now the thing that's being reduced is easiest because you can literally just look up aluminum 3+ going to neutral aluminum to find its reduction potential in your cell potential chart. But the thing that's being oxidized, you have to look it up and then you have to flip the sign. You might have remembered that we were already showing our copper up here. So we already actually looked up the cell potential for copper, and hey look, we already actually had to flip the sign. So we didn't actually have to go too far to find this value. Once we have those two values, easy enough to calculate the cell potential. So we get negative 2.00 volts. Don't forget about place value in sig figs. Hopefully you realize that because this is a negative number, this reaction is not thermodynamically favorable. Okay, we have just one more problem type to look at. It's very similar, but this time, instead of giving you two half reactions and providing you with the reduction potentials for each, did you notice that one of them was missing? Whatever will we do? Well, notice they did give you the overall cell potential for when you combine the two half reactions. So it's very similar, except this time we're going back and solving for one of the two values that we normally would just add to get to the cell potential. So let's try it. First, we want to start off by figuring out what's being oxidized and what's being reduced so that we can plug it into the cell potential equation. We know, of course, cell potential, you just add up the reduction and the oxidation half potentials, but we don't have both of those. So let's plug in the one that we know. So we don't have enough information yet to find the oxidation half reaction, but we did know what the overall thing should add up to be. So now we just, solve for the thing that's missing, the oxidation potential. Now here's where you have to be careful. That is the oxidation potential, but that's not what we were looking for. We were looking for the reduction potential for when lead 2+ is being reduced. So, easy peasy, we just flip the sign. That's it, not too bad. I bet you're excited to know there's another practice problem like that for you to try. This one you are gonna do. And when you are ready to check your answer, well, you know what to do. Unpause the video. So once again in this problem, we're plugging in all the values we know and solving for the missing oxidation potential. And then remembering to flip the sign to find the reduction potential. And that's it. So thank you for playing with all of the glories of tasty chemistry.